Jnanam Paramam Dhyayam. Knowledge is supreme.
In the general case, let us denote, let h and t be natural numbers such that height of q is at least h and transcendent degree of the residue fields kq over kp be at least t. Choose these are two non-negative numbers, so I will choose some natural numbers where this is at least h and this is at least t. H and t could be 0. So this height is at least h means there is a chain of length h in B, in the spectrum of B. So there is a chain Q0 contained in QH in spec B, and this is contained in Q. At Q is at least h, so at least there is a length of chain. This could be equal at the end. And similarly, about the transcendent degree. The transcendent degree is at least t means I have elements. So there are elements B1 to Bt in B. So and there exists B1 to Bt in B such that their images in the residue field P1 bar, Bt bar in KQ are algebraically independent over Kp. Over Kp. See, this is what I am using. The transcendent degree of this residue field at Q is over Kp is at least t, means there are elements which are algebraically independent over this residue field. So the elements here are coming from B. So that is what I call it B1 to Bt. Alright, now choose, because the chain is proper chain, I will choose at each stage an element which is not coming from the earlier one. So choose Ci in Qi which is not in Qi minus 1. This you choose it for I equal to 1 to h. Okay. You can choose an element here which is not earlier and keep doing it. So those are C's. And now I consider the ring B prime. This B prime is the algebra generated by these C's and these B's. So B1 to Bt, B1 to Bt and C1 to CH. Look at this algebra. See what the idea is, from a given situation you create a situation so that you prove for the subring which is finite type algebra, and then that is how the data is captured. No? So that is the idea. So now this B is a algebra of finite type, and the chain remains there, and so you contract the chain to B prime. So that means we have here Q0 intersection B prime contained in, and this containment remains proper because I have made sure that the element C's are also in B prime. So, this is in Q1 intersection B prime and so on. This is QH intersection B prime. That is why we put all the elements Ci in B prime. So, this is correct, and also the residue field, if I take this prime ideal, of course this is contained in Q intersection B, and if I take the residue field at this B prime, residue field at this, they actually contain all these B's also, because B's are in Q. So, this B1 bar, the images here BT bar, there are algebraically independent over Kp. I do not even need this, they are there. So, I do not even want to use this. So, what do I know from the earlier situation, finite type K algebra case, that the height plus the transcendent degree is less equal to height of this contracted ideal Q intersection B prime plus the transcendent degree of over Kp K of Q intersection B prime. This I know, this is the case from finite type case, because I am applying it to B prime, but this is less equal to height P plus transcendent degree of B prime over A, which is less equal to height P plus transcendent degree of B over A, because this transcendent degree may go up. So, that proves the inequality. Okay. So, I will remember that we have to still prove that that one inequality, that for that I will need little bit more local algebra, thing like system of parameters and thing like that. So, when I come develop that, I will come back to that proof. Now, I want to spend some little more time for the geometry part, which we will keep, which I have used in these exercises also. For example, the Hilbert-Schultz standards. So, the numbering here in the exercises, what I have done is, let me recall. So, the idea of the, so this recall this from this is the beginning of algebraic geometry. So, this, so for example, the problem is, so algebraic geometry is the study of solutions of finitely many polynomials in finitely many variables. So, it is a study of solution sets of equations like this f1, and f1 is a polynomial in x1 to xn, fm x1 to xn. So, and we want to equate, we want to find the common solutions. So, the standard notation for that is, and where, you see it is very important where you are taking, where are the coefficients and where you want to look for the solutions. So, I do not want to assume in the beginning itself that the base field is algebraically closed. I do not want to assume that, because then you cannot study, for example, equations or rational numbers, which are very important. So, we want to allow base field to be non-algebraically closed, but the solutions we will look for in algebraically closed field, because if you do not do that, then there may not be any solution. So, the typical situation what I will consider is K is a given field and I will take a bigger field than K. K is a L over K is a field extension, and in this I will assume the bigger field is algebraically closed, L is algebraically closed, and therefore, when I look for the solutions, I look for the solutions in L with coordinates in L. So, therefore, the notation one uses will be VL, just to remember that we are taking the solutions in L. VL of F1 to Fm, this is by definition all those points A is A1 to An in Ln such that all Fi's vanish there for all I. This is some subset of Ln, and this is called algebraic K algebraic set defined by F1 to Fm. We are also keeping track of the coefficients where they are lying. So, for example, the Fermat's last theorem so that was asking what we know is over C there are infinitely many solutions, but over Q the solutions where we wanted to show that the over Q they are only finitely many and which are they. So, that was the problem. So, later on I would even want to drop this condition where K is a field and replaced by integers or arbitrary ring, but those will require more sophisticated tools. We will see at the end if it is possible. So, VL also now obvious things you might have checked earlier that this VL depends only on the ideal generated by F1 to Fm. These will not change. The solutions will not change because any other polynomial in the ideal is a linear combination of that. So, in other words, I can always concentrate only the ideals in a polynomial ring in n variable. So, therefore, we are considering only ideals in K x1 to xn, and we have given a map VL from this ideal set to K algebraic sets in Ln, which you think it is a subset of the power set of Ln. Alright. So, and also immediate that this VL does not only depend on the ideal, it depends only on the radical of that ideal. So, we might shrink these ideals to radical ideals, because once you know for the radical ideals you know. So, therefore, I will consider this VL map from radical ideals in K x1 to xn to K algebraic sets in Ln. And also it is, you might have checked earlier that these K algebraic sets form it defines a topology on Ln where you declare the closed sets in that topology are precisely the algebraic sets. So, those things I am not checking. So, I am assuming those. So, this is our VL map, and we have a map in the other direction, namely. So, given a K, actually the map is again like this map, it is from arbitrary set. If I have arbitrary set W of Ln, Then we have the ideal ik of, now I have to use this ik also in the notation because we want to keep track where the equations are. This is by definition all those polynomials f in the polynomial ring such that f is 0 at every point of w, f of a is 0 for all a in w. Now, one checks that this is an ideal, that is obvious because if f vanishes, g vanishes, then f plus g also vanish, and arbitrary multiplication by arbitrary polynomial also vanish. So, this is actually an ideal, not only ideal, it is a root ideal. That is also clear because if a power of a polynomial vanishes at a, then that polynomial also vanish, because see f power n is f a power n, and in the field we are. So, therefore, f a's are 0. So, therefore, this is a root ideal, this sometimes I will call a radical or root ideal, that is same as this. So, therefore, we have a map in the other direction, namely this ik, and then we want to know when these maps are inverses of each other, and that is precisely when, if L is algebraically closed, then these maps are inverses of each other. So, when L is algebraically closed, then V L and I K are inclusion reversing inverses of each other. Obviously, this VL, if an ideal radical ideal A is contained in radical ideal B, then VL will reverse the inclusion. Similarly, this ideal. Okay, then to this we write the consequences, namely, so what I call this is HNS1. So, for example, what is the criterion that given any ideal, VL of that is non-empty? See, it is not clear whether VL of an ideal is non-empty. So, HNS1 says if L is algebraically closed, then and VL of A is non-empty if A is a proper ideal. That means there is at least a one common solution. So, this is like linear algebra. You see, if all were linear polynomials, if all these Fi's were linear, then we know from linear algebra that the system of linear equations is consistent if some condition, right. So, similar to that. So, this is A is a proper ideal. So, also I forgot to mention that any ideal is finitely generated, that is why Hilbert proved the Hilbert basis theorem, that only finitely equations are needed to define an algebraic set. Okay, so, HNS2 that says if I take VL of an ideal A and apply IK to that, then this is some ideal, and this ideal is, if A is a root ideal, then this ideal is A, otherwise we will have to write root A here. So, let me write root A here. So, this is usually called, if you see the books, it is called a geometric form. The first one is, I do not know, it is called a weak form, and then HNS3. So, this is again under the assumption L algebraically closed, and both these are not true if you drop the assumption L algebraically closed. Okay, and third one is simple. Third one is more easier to state, easier to prove. So, K E over K, the field extension, K is our base field, E over K is the field extension, and E is K algebra of finite type. Then K is E is algebraic over K. In particular finite. E is a finite over K, that is the dimension as a vector space is finite. So, actually these formulations HNS1 equivalent to HNS2, HNS3 and equivalent to HNS2, they are equivalent. These also I am not I do not know whether you have you know the proofs individually probably, but you do not know the proof of equivalence. So, I will write in the notes, you can read there. And also if you remember we have stated the fourth one, it is there in the exercise sheet, HNS4. It is you remember if K algebraically closed, then SPM K x1 to xn and Kn. So, there is a map, obvious map is in this way, given a point A equal to A1 to An. You take the ideal generated by x1 minus A1 etc. xn minus An. This is the maximal ideal at a point A, and this map is obviously injective. This is injective, that is clear, but if K is algebraically closed, then this map is actually bijective. And if K is not algebraically closed, this is false. For example, if I take K equal to real numbers, n equal to 1, and if you take the ideal generated by x square plus 1, this is a maximal ideal. But it is not coming from a point, but not in the image. Our map. You see, no wonder this polynomial does not have a 0 in R. That is why HNS1 also fails, HNS2 also fails, and HNS3 also fails. And HNS4 is also equivalent actually. HNS3. Once I prove to 3, you see the easiest to prove is 3, because it is a field theory, So, this also you can, it's written as an exercise here. So, you can try to check.